Welcome back to solving system equations by graphing. We're on example 2 where we have to graph the following equations and determine the solution to the system. Okay, so let me remind you that both of these equations, because the y is by itself, are both in slope-intercept form, where y is the output, the slope or the coefficient of x is the slope, and then we add or subtract the y-intercept. Okay, so the first thing we need to do is we need to step 1, we need to graph. Okay, but what is step 1 of graphing? The first thing you do is you plot the y-intercept. Let's do the purple first. So if we're looking at the purple equation, we need to identify our y-intercept. It's the number by itself with no x next to it, so it's 4. So we're going to start by plotting 4 on our graph. Right there, 1, 2, 3, 4, there it is. Step 2 of graphing in slope-intercept form, as a reminder, we're going to use slope to find other points. Okay, so in this case, we need to identify our slope. Our slope is the coefficient in front of x. It's 1 over 2. We like it in fraction form because that is the rise over the run. So what that means is we're going to go up 1 unit and we're going to go to the right 2 units. If it was a negative, I like to think of the negative going to the top, and so we go down. I always like moving left to right. But in this case, it's positive 1, so we go up 1 and to the right 2. Up 1 to the right 2. Now, you start from your y-intercept. You don't start from the origin, you start from your y-intercept. You go up 1 to the right 2. I like to do this multiple times so we get an idea of where this thing's going. And I like going in reverse too, so I like to start in here. Instead of going up, I go down, and it's going to the right, I go left. We can do that because we get the same point, okay? Now it just becomes a matter of connecting our dots to see how well I can do. Not bad for a first go. Usually it takes me a couple times, but that was pretty good. So we graphed our first equation. Next thing we have to do is we have to graph our second equation. This too is in slope-intercept form, because the y is by itself. So we're going to look first at the y-intercept. The y-intercept in this case, -1. So we're going to go to our graph where -1 on the y-axis. There it is. Okay. Now we're going to use our slope. Our slope is the number in front of x. I like to put it over 1 if it is an integer, so we know what our rise over our run is. Remember, we rise with the y's, run from our x. So we're going to rise 3 units, and we're going to run 1 unit to the right. Now, the whole point of putting multiple dots, yes, you only need 2 dots to make a line, but I like putting multiple dots because then it becomes easier to see where the lines intersect. So again, I went 1, 2, 3 up, 1 to the right. That's where I landed. I'm going to do the same thing. 1, 2, 3 over to the right. What do you know? I land on the same point, and that's why I like to plot multiple points. I could have only used 2, and then I might be guessing and not be as accurate, whereas if I know I land on the same point, I know that's a little bit more clear. Okay, again, I can go in reverse. Oops, go down 3 to the left 1. I'll connect my dot just to be thorough here, even though I know where the solution is. Okay, and my solution is here. That is the point 2, 5. That means the x value is 2 and the y value is 5. What does that mean? Well, if you were to plug in this x into both equations and plug this y into both equations would come up with a balanced equation. They would both be satisfied by the solution. What does that mean? Well, we kind of saw in our previous example when we plugged it in that the 5 equals 5, 5 equals 5 for both equations, and we saw that checked out. So it's the same thing. I'm not going to show it here, but if you plug in 2 for x and 5 for y, both equations, you'll get a true statement, so it is the solution. Now what happens if you use a point like this, for example, which is the point 0, -1. If you use this point, it will satisfy the green line. Okay, it will make a true statement. If you plug in 0 for x, you get -1 on the right side. If you plugged in -1 for y, you'd get -1 on the left side. That is a true statement. Bingo. But if you were to plug it into the purple equation, it would not be satisfied. That's why 0, -1 is not a solution, because it is not satisfied by a single x and y value. Okay, so it's where they intersect, which is clearly 2, 5. And that's how you do example 2. Moving on to systems vocabulary, we'll see that there's two main types of systems, and there's consistent, which means at least one solution. Inconsistent systems have no solutions. Now, let's take a closer look at consistent systems. Okay, they have at least one solution, so that means there's probably multiple types. The first type is independent. That's what we've kind of been doing. There is one solution. Only one solution. Okay, so there's only one solution because they only intersect at one spot. What about dependent? If it intersects and it doesn't intersect only one spot, that must mean there is infinite solutions. So if we look here, we can kind of see that there's a red line, there's a purple line, and where the orange is everywhere they intersect. That means that they're the same line or equation. So if they're the same line, that means they overlap. They have infinite solutions. Every single point along those lines is something that satisfies both equations. Now let's look at inconsistent systems. What do you notice about the green and the orange line? I hope you notice that they have the same slope. Okay, they are parallel lines, and that's inconsistent. They will never intersect, so they'll never cross. They'll never have the same values of x and y that satisfy both equations. Now in Algebra 2, another way that you can have no solutions is skew lines, but we're not going to talk about that in Algebra 1 because that's in 3 dimensions. Okay, hope you learned something. We're going to be moving on to one more example in example 3 after these messages.